So when we're taking determinants, we found that if we had a large matrix, that it's helpful to have a lot of zeros and or ones in a row or column. Um, so when you cofactor expand that row or column, you get terms that drop out. You get easier calculations. So can we create those zeros using row operations and still maintain the determinant? Will the determinant be the same if we start doing row operations? So the answer is yes and no and no. Okay. So of the three row operations you can do, so there's interchange rows, right? You can multiply a row by a constant. And you can add a multiple of one row to another. Right, so these are the three things you can do when doing row operations. So how does this affect the determinant? So for interchanging rows, it changes the sign of the determinant. If you switch two rows, then the sign of the determinant will flip. So if the determinant was -12 and you flip the sign, then the determinant of the new matrix will be +12. So you just have to know that when you get done taking the determinant, that you need to multiply by -1 to reverse that. If you multiply a row by a constant, the determinant gets multiplied by the same constant. So if you multiply a row by 2, because you're taking every entry in that row and doing the cofactor expansion, every entry gets multiplied by that 2, so the whole determinant gets multiplied by 2. So if you do that in your operations, you just have to know that when I got done, I would need to divide by 2 to reverse that determinant, to reverse that row operation that you did. So the good news is on number 3, if you add a multiple of one row to another, this does not change the determinant. So that's great. So you can always add a multiple of one row to another, and it's not going to change the determinant at all. And there's nothing to keep track of. So let's do an example where we use this. So we have the determinant of a 4x4 matrix. And if you see these long straight lines outlining the matrix, that means you're taking the determinant. So it's kind of instead of writing determinant, you can just use, it's almost like absolute value symbols. That means take the determinant. So now I want to see if there's anything I can do to get a bunch of zeros in my matrix. So one thing I could do is let's do this. Let's add the third row to the second row, right? So this is equal to the determinant of this matrix. So I got to figure out, I got to decide which one I'm going to add. I'm going to add the second to the third to the second and change the second one because I don't want to get rid of this 0 here, right? So I'm going to leave the third row alone. And I'm going to add third row to the second, and these 3's will cancel out. So 0 plus negative 9, and then 1 plus 5 is 6, and then negative 2 plus 10 is 8. Okay. What else can I do? Well, I've got a 2 up here in the top left corner. If I could divide this row by 2 and then pivot and make all the entries 0, okay? But then I would have to divide my determinant by 2 in the end. So instead of doing that, I've already got a 1 here, and I'm not even going to interchange rows because that's going to change the determinant as well. If I just use this 1 and eliminate the other entries in the matrix, then I'm not going to change the determinant at all, and I'm going to have all these zeros. So let's try that. So let's write down what we're going to do. We're going to replace row 1 with row 1 minus 2, row 4. And I'm going to replace row 3 plus 3, row 4. Okay, so this is going to be equal. I don't have to adjust the determinant at all because I'm just adding a multiple of one row to another. So the row 4 doesn't change, and looks like row 2 doesn't change. So let's do the first row. So 2 minus 2 would be 0. Negative 8 plus 8, that's also 0. 6 minus 0. 8 minus 12, so that's negative 4. All right, so let's do the third row. Negative 3 minus 3, 0. 0 minus 4, no, that's 0 minus 12. 1 minus 0. Negative 2 plus 18 be 16. So we can see that I have a 1 here and zeros everywhere else in this column. So I'm going to cofactor expand this column. And let's remember the sign matrix. For that entry, we need to multiply by negative 1. So this is going to be negative 1 times the determinant. And I'm going to take out the row and the column that 1 is in, and I'm going to take the determinant of what's left over. Is there something I can do here to give me 2 zeros? So I have a 0 here, and that's in this row and this row and this column. Don't really see anything to create a second 0. I could use this 1 and eliminate both of these 6's, and that wouldn't change the determinant. So let's do that. So I'm going to replace row 1 with row 1 minus 6, row 3. Going to replace row 2 with row 2 minus 6, row 3. I'm not trying to row reduce this to get to get a solution to a system. I'm just trying to make the determinant easier. So row 3 doesn't change. So for row 1, I'm going to subtract 6 row 3. So 0 plus 6 times 12, that's 72. 6 minus 6 is 0. Negative 4 minus 6 times 16, that's going to be negative 100. So 6 times 16 is 96. So negative 4 minus 96 would be negative 100. In the second row, negative 9 plus 72 It'll be 63. 6 minus 6. 8 minus 96. Negative 88. All right. So now I have this column with a 1 and 2 zeros. So I'm going to eliminate that row and that column that 1 is in. It's going to be negative 1 times, and remember, where's the, what's the sign here for this one? So this is a 3 by 3 matrix. In that position, I need to multiply by negative 1. So I'm going to have another negative 1 here times the determinant of 72, 63, negative 100, negative 88. So these cancel out. So this is 72 times negative 88 minus 63 times negative 100. Let's see what that is. So this is negative 6,336. I got two negatives here, so that's a plus. So this is 6,300. It's like the answer is negative 36. Now, did I do more work than it would have been to just do the determinant and not do the row reductions? Maybe, maybe not. But if you are having trouble taking determinants, then you can use row reduction to make it easier. So some other properties of determinants. If you take the determinant of a product of two matrices, it's the same as taking the determinant of one matrix and multiplying it by the determinant of the other. The determinant of the transpose is equal to the determinant of A. So that makes sense because you can cofactor expand any row or column, and when you take the transpose, you're just switching rows and columns. And then if A is invertible, then the determinant of A is not equal to 0, right? So that's something that we've talked about in the past. Okay, so just something to remember. So let's just look at some of these. Let's find the determinant of A and the determinant of B, and we'll see if it's equal to the determinant of A times B. So the determinant of A would be 12 minus 3, so it'd be 9. The determinant of B is 8 minus 3, so that's 5. Let's compute A times B and then find the determinant. So let's see here. We've got 24 plus 1, so it'd be 25. 18 plus 2 is 20. 12 plus 2 is 14. 9 plus 4 is 13. So that's A times B. Then we're going to find the determinant. So it'd be 25 times 13 minus 14 times 20. So this is 325. I'm just using a calculator here. This is 280. That's 45. So the determinant of A times the determinant of B is 9 times 5. So that's also equal to 45. Right, so these are the same, right, just like this says. Right. Okay, what about inverses? If you have an inverse, let's say A times A inverse is going to be equal to the identity matrix, right? And if I take the determinant of both sides, the determinant of the identity matrix is just 1, right? Because You should do that yourself. Take the determinant of an identity matrix, see what you get, but you're going to get 1. A times A inverse, so by the property we just talked about, that's the determinant of A times the determinant of A inverse. This is assuming the inverse exists, by the way. So all I have to do is divide by the determinant of A, and I get a formula for the determinant of the inverse. So if I know the determinant of A, then I automatically know the determinant of its inverse is going to be just the reciprocal of the determinant of A. So let's take one of these and try it out. So 6, 3, 1, 2. So A is 6, 3, 1, 2. The determinant we found was 9, right? So what's the inverse? So A inverse is 1 over the determinant times the adjoint. So that's 2/9, negative 1/3, negative 1/9, and 2/3 when you multiply the 1/9 inside. Let's find the determinant of A inverse. That's 2/9 times 2/3. That's the main diagonal, minus negative 1/9 times negative 1/3. So that's 4 over 27. And I've got 3 negatives here, so it's going to be minus 1 over 27, which is 3 over 27, which is 1/9, right? And our determinant of A was 9, so the reciprocal of 9 is 1/9. So yeah, that property works as well.